All right, thank you everyone for attending this talk today. Before we begin, a little bit about myself. My name is Matthew Otterberg. I'm a technical manager here in Optus Threat Management team. Part of that role involves running the breach services. This is our adversarial simulation group focusing on red teaming, purple teaming, and emulating nation threats. I've also authored numerous open source tools as well as frameworks. Put a lot of focus on research, specifically around EDRs, evasion, and as well as bypassing other security controls. I've spoken at DEF CON's Red Team Village, DerbyCon, B-Sides Las Vegas, ScareCrow, and RSA. Before we begin, a bit about the agenda. We'll kind of go through several different topics, including understanding avoidance, um, then actually going into the techniques to bypass EDRs. We'll cover some of the new techniques introduced into ScareCrow. Then really kind of focus in how we stay silent when we blend into the background. We'll kind of demonstrate several tools as well as kind of wrap it up with some recommendations and questions and answers. So let's begin. I like to begin with understanding the defensive structure, and I always look at it from three pillars. First one, obviously, being the frontline endpoints and what's kind of really installed on them. A lot of times these controls are, EDRs, antiviruses, whitelisting mechanisms. They're very proactive in nature and very preventative. They lock down when certain behaviors or signatures are met. They also send a large amount of telemetry to that tier 2, the blue team, so whether that be an MSS, SOC, or SIM. This is really where a human kind of comes into play, reviewing these events. Oftentimes, these products in tier 1 may miss something, or something may not stand out as suspicious or needing to be investigated, that when reviewed by a human will clearly indicate that there is a threat. However, with any type of interaction or inclusion of a human element, there's often false positives. This is where the tier 3 kind of comes in. They usually only ever get involved in defense when there's a huge escalation, such as a massive threat or the blue team is overwhelmed by a threat actor. The reason why they they're so damaging to a threat actor is because they know everything. They know the playbooks, they know the techniques, and they also know that there's an active threat. They're not looking for a threat. They know there is one. They're looking for the breadcrumbs to help understand where that threat has gone, what the threat has done, what level of access, and what's the impact. So once I understand this, we can actually start really focusing in on EDRs and the next gen of protection that they offer. Briefly, and we'll dig more into this, this is an example of how that telemetry would typically flow. So you have your platform, this is like your dashboard in the cloud, your agent that's installed on an endpoint. This agent has a lot of those policies, rules, and protective controls that are implemented. Then you have this DLL. This DLL is loaded into the process's memory. Every time a new process is spawned, this DLL is loaded. This allows for the telemetry to flow from the process to understand what's going on in there, whether it be an injection or some kind of malicious behavior. This DLL really kind of helps the agent and everything else all together in the security suite understand what's going on in memory to make those decisions and to feed that telemetry over to the agent and then to the dashboard. It's very important to note that the agent really handles those preventative measures defined by the policy, but the deep intellectual advanced threat analytics happens usually in the dashboard or that platform. So before we go any further, we should really kind of define two terms. First one is WinAPI functions. These are functions that are used to interact with operating systems resources. This can be such as being able to create a file, save something, load a picture, copy something onto a clipboard. A lot of these types of low-level functions are handled by the WinAPI. This sets up all the resources, the registers, and everything like that, so the right data is in the right place. A lot of these functions are in kernel 32 and kernel base. This functionality was really introduced so that way when a program is developed or anything like that, they don't have to bring this with them. This is something that's native to the operating system that can be used by any program, and there's a lot of stability. The next one is the system call instruction. This is a low-level assembly instruction that actually handles the process of taking whatever data is in those registers that the function has aligned and actually performing that operation on the CPU. These are as low as you can get before you get into the kernel, and these are stored in anti-DLL. So here's a bit of an example of how that execution would look. So let's say we have an application called app.exe, and it calls virtual allocate. Well, virtual allocate is stored in kernel base. So this function will then perform a series of things to make sure all the registers are aligned with the right values, and then pass it off to anti-DLL, where the actual system call related to this function is stored. In this case, it's anti-allocate virtual memory. It will actually perform the process of executing that system call, which will then be moved into the kernel mode. The instruction will then be executed. Based on what the response will be then sent to anti-DLL and then passed over to kernel base, where it clears the registers and either based on the command, if it's successful, we'll move on to the next instruction, or if it wasn't, it will throw up an error. Now let's look at that same example, but with an actual EDR involved. So we have that same app.exe, it's going to call virtual allocate. However, when we get to kernel base, we'll notice that there's a redirection or a jump instruction. This jump forces the execution flow to go instead of from kernel base to anti-DLL, but instead to the EDR. And this is how the EDR at a low level understands what's going on in the process. It can see, okay, this function has been called. This value is in the registry, the register, sorry, and all these different values. And based on that, it can actually read and understand what's going on. If it's okay, it will return that instruction and allow the execution to continue on. It does this typically with the function and the system call before it gets into the kernel. Now there are two different areas where this hooking can occur, or in the user space or in the kernel. Now, predominantly, a lot of products use the user land. There are many pros to this. First one, obviously, it's more stable. There's less issues of crashing or causing problems. It's also really easy to integrate with other products such as SIMs or anything like that. When you are looking at all that information in telemetry, you want to have a wide spread rather than a very narrow focus. And being able to use the user land is more stable, which means there's going to be a lot more integration. The kernel, however, is a lot more resilient to attackers or threats. Because of the nature of the kernel, you can't just simply modify anything in there. You typically need to have some sort of driver. And this driver, with the latest additions and modern controls that Microsoft has implemented, has to be signed and verified by them before it can be even allowed. Also, there are several things such as patch guard that makes it really hard. Because of this, it has a different perspective, whereas in the user land, everything's moving into the kernel. In the kernel, everything is there before the actual operation occurs, so it has a different perspective. Now, there are pros and cons. In the kernel, there's always going to be a stability issue. When you're interacting with anything at that kernel level, there's a high chance there could be you could crash or blue screen the endpoint, which causes problems. There's also an issue that there's not the same level of telemetry or different functions that there are in the user land space. Ultimately, the downside of userland, though, is that it's easy to subvert or modify. This is simply because anything in the userland space has the same permissions as anything else. So if this process is run as a normal user, everything from the actual code to those userland DLLs and everything else has the same permission. This ultimately means that we can actually manipulate anything in those spaces before we actually do anything malicious, including tamper with the hooks installed. Now we're going to take a deeper look at these hooks and the EDRs themselves and understanding how they operate at a very low level. So first off, we have to understand what EDR, what it's doing in that DLL. This often can be involved by just simply looking and understanding and seeing, oh look, this EDR has loaded this DLL. It might be sometimes more advantageous to have to go a bit deeper, such as looking at the name, knowing that this DLL name is related to a certain EDR product. You can also tell by looking at the path of where this DLL resides on disk. If it's in C program files, a known EDR name, that's usually an indicator. There are also sometimes where you can look at the code signing cert that's attached to these DLLs. However, some products out there are moving towards having their DLL signed by Microsoft. That's a security measure. It's not a obfuscation or evasion, but it's just a way around some techniques that are out in the wild. But once we understand what the DLL's name is, we can actually then move forward and actually navigate into our process's memory and look for any jump instructions that go to that DLL. A jump, or E9 in in assembly, is really referred to as a redirection of the instruction or execution. So whenever we see a jump to this DLL, we know that something's being redirected to this DLL. And with that, just by simply searching for E9, we can see all the hooks that an EDR product has in our process. And this can kind of look like this. You can kind of see right here at the bottom, we have our normal, what they should look like with that RC10, RCX, EAX, 1A. That looks like a normal instruction. You can see it goes 1A, 1B, and 1C. But right above it, we can see that the two instructions have been hooked with that jump. So that usually is a big indicator, because a proper system call should be move RC10, RCX, then followed by move EAX, and then a value depending on which syscall it is. So now that we know which ones they hook, we can actually understand what techniques would be successful, what telemetry they gather, and ultimately understand the weaknesses, especially from a post-ex perspective. But with all this information, we can now actually move into understanding how to bypass these products. So the first technique we call bring your own system calls, or syscalls. This is actually the act of writing that assembly that I just described, that move RC10, RCX, all that code, bringing that with us in our process. But instead of calling the endpoint's version, we set up all the registers ourselves using our code, then actually perform that system call function. Now, with that, we go around the hooks. So rather than calling and they get triggered and everything gets reviewed, if we set up everything that it's supposed to be and then go around it to still perform that same instruction that gets translated into the kernel, we've gone around it to bypass it. There is some caveats with this. System call values are dependent on the Windows version. So with Windows 10, it might be 18 for anti-allocate virtual memory, but in Windows 8, it could be 17, and as you go down. So it's really important to understand when you're attacking or building these types of mechanisms to understand that the system call is very dependent on the version of Windows you're running on. Another technique is just simply dumping the EDR out entirely. So we know that an EDR hooks a process when it's spawned. And we know what the DLL hooks, which is those three processes, kernel base, kernel 32, and NTDLL. What if we just reloaded them? Well, it's not as simple as that, because for one reason, you can't have two of the same DLL loaded in. It makes the process confused. You can't understand which one to use, and ultimately it crashes. However, we can't first unload those DLLs from their process, because when we do so, our process loses the ability to interact with the operating system. So this is where it gets really interesting. We can use an API called Virtual Protect. This actually changes the permissions of a process's memory. That can even be a section or a thread. So we can take areas that would normally read execute and make them writable. And once this area is writable, we could start writing our own version into those sections. Where would we get a clean version? Well, there always has to be a clean version of these DLLs, because that's the one that they're being loaded from. It can't be manipulated, massaged, or changed, because then there would cause instabilities and crash the whole system. So these system DLLs are stored in system 32. So now that we know where a clean version is, we know that we can change those permissions. We can actually write the entire DLL into our memory processes section where that DLL is by writing and reading those raw bytes. So this is where we now take it a step further. Instead of taking the whole DLL and reading those raw bytes and writing it in, if we just change a small section of it, the .text field, we can essentially avoid any type of triggers or alerts, which we'll talk about in a little bit. But we also can ensure that there's stability in our process. The .text field is where all the executable code is stored. In the case of a DLL, that's usually where all those functions or exports are located. So if we're just looking at there, that's where all those functions, such as system calls or Win API functions, are stored. So since we know that, we just have to change one segment of a DLL in memory in order to remove all those hooks. So it's not as simple, especially with modern systems. With the introduction of ASLR and other things, memory addresses are not static. So it makes it hard for us to read it and make sure that the bytes that we're writing are in the right place. However, we can use the offsets that are stored for each function or system call to make sure we're aligning everything correctly. An offset denotes a number of addresses from the starting point, or the base address, in order you have to go to hit that right and absolute address. So in NTDLL, if we wanted to find out where ntclose actually sits, if we know where the base address of ntdll.text field is, and we know that the offset number is 96B40, if we increment that many addresses, we will get to ntclose. So by incrementing and doing that, we can properly align everything so that way when the process resumes and the next actual instruction is executed, there's no stack alignment or any type of issues there. So this is how it actually would look. You see we have in the middle our DLL that's running in memory and it's hooked. But we know that system32 is where all those DLLs are that are clean. So we read in that file, take that .text section, overwrite it. We now have a clean DLL that's running in memory. So you can see right here, we have our hooked NT allocate virtual memory. But after it runs and is reloaded, we can see what I mentioned before, that RC10, RCX, EAX 18 value has been restored. So there's no more any hook, there's no jump instruction. The EDR hook has been removed. Now, probably asking, what about anti-tampering? Well, there's a lot of products introduce anti-tampering controls. Not all of them. But anti-tampering prevents us from doing what I just described, because obviously to do that we have to call those functions such as virtual protect. If virtual protect is hooked, they're going to see what we're doing. But if we introduce that technique that we described before about bring your own system call, we can write our own virtual protect memory to do that same function at the system call level, and we can bypass those tampering controls to first remove those hooks without triggering the anti-tampering, and then load our shell code without being caught. So now I'm going to talk a little bit more about the new features that will be introduced into ScareCrow. So the first one is process injection. Previously, ScareCrow would create binaries or sideload into processes. With this introduction, we can now do process injection. Now, I know you're probably wondering, but if you create a new process, that DLL is just going to hook it. That's okay. So the first thing we're going to do is perform the same set of instructions, so remove the hooks that we just talked about. Once that's done, we're going to create a process and get a handle to it. A handle is a pointer or a reference to something, in this case the process. But we also can have a handle to a module, which is a DLL, or even a handle to a module's base address. So once we do that, we can call another set of functions, enumerate process modules. So we know that kernel base, kernel32, and NTDLL have been loaded in that process. And once they have been, we can then use get module information using those pointers to get the base address. Now, once we have that base address, we can perform the same steps we described previously about rewriting in that text section of memory. However, this time we're going to use write process memory. Once that's done, it will have unhooked and basically restored those sections to be what I like to call clean, free of hooks. And then ultimately we can inject our shell code into that process. This is really important to note. So why we use write process memory? Write process memory has a lot of great conditions and caveats. The condition I'm referring to is a race condition, that if a process is being manipulated, even if the protections are set to read write or anything like that that would normally prevent it, if everything in the function call is correct, write process memory will make a temporary change to allow that execution through. This is ultimately done and intended for an audience of debuggers or programmers when they were looking at patches to improve. Rather than recompiling a program completely, being able to hot fix and change something on the fly allowed for a lot more ease as well as speedier return on patches. Because of this, we can use the same thing to set up and align every write value, change the permissions of another process's memory, in this case the .text section of all those DLLs, read in those bytes, and it will automatically restore the original permissions without us having to call it a second time. This also it can be used for both remote processes but also local. But for this focus, we're really going to be using this for remote processes, and I'll show an example of that in a little bit. Another new feature, and I'm going to kind of talk about it in a second, but before we go there, we need to understand what we're doing or manipulating. So the first thing is understanding what event tracing for Windows is, or ETW. It's a mechanism that lets security products log events. This is different than the telemetry you get from hooking Win APIs or system calls. Rather, these are events that can be used by anything. They're often used by products as a secondary set of telemetry. There are some products that solely focus on this by living in the kernel and just consume the events based on what's being defined by a policy. There are three major things that are involved here when understanding ETW. That's first the providers, the controllers, and the consumers. The providers are our process or any type of application that can generate these events. This could be, create process, load library, call this function, anything like that. A controller dictates whether or not an application's events are going to be logged, or which rules and events will be kind of logged. And ultimately, a consumer is what consumes those logs from a process to make those the rules and definitions. It's very complex and detailed, but from that high level, we have enough information to kind of go into our next set of discussion points, which is patching it. So one of the unique things about ETW is that there's no need for a hook, as I mentioned. These are all these functions exist in NT-DLL already. That controller dictates what events are going to be used or enabled. So because there's no hook, we can't really unhook it. However, to prevent that telemetry, we can simply patch the ETW events in our process to prevent the transmission of data. Now, looking at the example below, we can see that this patch has been applied. So the first thing this patch does is it XORs the RAX register. The RAX register stores the value of any returned pieces of information from a function. This often is if this event is called or this ETW function is called, it will return the response. By zeroing it out, there is no value. And then that last one, ret, will just return to the next instruction. So just by doing that simple thing, we can terminate the telemetry sent or generated by ETW. So blending in. So we've bypassed the EDR. That doesn't mean that we can't be detected from other things. There are many other log-based systems or mechanisms that a SOC, SIM, or MSS can be plugged into that, when reviewing those events, can lead to an investigation of our activity. I always like to say, EDR may not think AW2R 1941G.exe running from app data is suspicious, but a human who looks at that might start investigating, and that might ultimately lead to our detection and then being caught. So, in this example, we had a payload that was loaded into a process. The EDR did not trigger, but from a post-mortem review, you could clearly see there was a lot of suspicious indicators, such as every DLL or everything that was loaded in was signed, except for ours. And when you looked at any type of metadata or anything like that, or file version, there was nothing. So this really kind of lends itself to say, well, this stands out. I need to investigate this and to see why. And that usually is often why we get burnt on our red team ops. So how can we avoid this? The first thing is implementing a code signing cert into our binaries or DLLs. Files that are digitally signed draw less scrutiny. EDRs don't usually have the capability to do a full verification on a cert. If the cert has a lot of the right values, it's going to allow it through because it believes it's trusted. Now, code signing certs aren't cheap or easy to really get, and often can be burned if they're identified as part of a malicious campaign. However, we have to be very cognizant about that, and as a result, we don't necessarily need to have a full code signing cert to still be effective. This is where a tool, Limelighter, comes into play. Now, this tool is publicly available, and I'll have a link at the end if you want to take a look at the project. But this is a tool used for signing binaries and DLLs. It takes the attributes of a domain that you specify and grabs enough of the information to sign it, to make it look like it is signed by that domain. It even has this issuer, the serial, all those types of things that a typical EDR would check for. Now, another feature it can do is if you do have a legitimate, a real code signing cert, you can actually take the values of that and use it to sign any type of application, DLL. It could be a post-ex tool, an initial foothold type of tool. It's really designed for that because, as I mentioned before, these draw less scrutiny. Now, the other issue in that example, file attributes. So let's talk about that. Having no attributes or the compiler's information, such as the system was compiled on, the user, or anything like that, can be an indicator. However, having nothing can be worse. And that's ultimately the issue here. Really is that if it stands out, it's going to lead to someone investigating it. So using something called syscalls files, we can actually dictate when a file is being compiled what can be done, or in this case, what attributes it should be writing to the file. This also means that we can overwrite certain attributes, such as file version, the owner, the file's name, other attributes like that. Not all languages can handle syscalls files, but the important thing here is that this is really useful when we're trying to blend in and tell a story to not stand out. So how can you get these types of files? Well, from values from a file, well, any endpoint, you can simply use PowerShell to get the version information, as you can see right here. And you can see it using Notepad as our target example. We can see the version, the path, the copyright, all these types of attributes that would make our file look like Notepad. Once we have these attributes, we can actually go ahead and store them to be used in a syscalls file. And this, it can be used for a lot of great things, such as generating, DLLs, binaries, or anything like that. We really just need to focus in on what would be on pretty much every endpoint. That can be system DLLs, Office binaries, typical things like Adobe, Google, Chrome. And it's important, as you can see right here, to generate a large list. Using the same attributes over and over again can eventually get that set of attributes or that file burnt. So by creating a rotating list, you're always changing it, and by doing so, you're always staying one step ahead. So it looks like this file was first was Word. Now it could be PowerPoint on the next time you generate it. So they're two different. They don't look the same, and it really makes it hard for any type of human operator to investigate, to say, wait a second, I need to investigate this. So let's examine. There's 4 examples of 4 different files. Can you tell which ones are real, which ones are fake? If you said all of them are fake, you'd be correct. That's how hard it is. We can spoof the original file path, the language, all these different things. It makes it really hard to discern what is real and what is malicious. So with all these aspects I've talked about, I'd like to introduce ScareCrow. ScareCrow was released back in February as a framework to utilize to bypass and flush out hooks from an EDR. At its initial inception, it would reload NTDLL, kernel base, and kernel 32. It still focuses on that, as we kind of discussed. Those are where all the system functions are stored that are constantly being hooked by products. Once, as well as to unhook, but once it's unhooked, ScareCrow uses custom system calls to load and execute shellcode. The shellcode is stored in an AES encrypted format, making it harder to signaturize or detect. The other major thing is it doesn't use standard ways to execute, such as virtual allocate, virtual protect, write process memory, etc., etc. It uses alternative ways that are not commonly found in the wild, making it harder for behavioral or other events to trigger on what's going on, even if it's such as kernel-based security tools that can see all these events. Now, ScareCrow can create a binary, but also uses various techniques to sideload into a process. Sideloading is the act of actually spawning a process, forcing it to load this malicious DLL. So in some cases, you can see this with WScript, Excel, or even run DLL32 with control panel applets. But as I mentioned before, with these new techniques and that will be released shortly after this talk, we can now also do process injection. We can also patch ETW. Now, as of today, the ETW patch currently only will patch the primary process, so it will not work well with process injection. I'm hoping to get that released in a little bit, so please stay tuned. But really, these are a lot of things that have already been publicly used in this repo with a few new features. Now, I mentioned before sideloading and binaries, but when you actually use ScareCrow, there are multiple different what we call loaders. Loaders are the way of loading and unhooking that shellcode and our process's memory. So the first one is binary. This one just creates a standard binary. It's an executable. When you double click or you launch it, it runs. I mentioned before about run DLL and control panel applets. When you specify control, it actually will use the .cpl extension with specific DLL exports that will allow it that when it's executed, it will actually spawn run DLL and then load it in. This is partly related to the control panel applets. A DLL just uses a straight DLL based loader. This requires things such as a reg server 32 or run DLL in order to load it into memory. Excel creates an actual Excel plugin that uses JScript to load in the plugin, spawn Excel, and execute it. Now, a new feature that's new as part of this release will also be MSI exec, where we'll use MSI exec to actually spawn a process and then execute the DLL. The last one is WScript, which uses a registration-free COM technique that will use a manifest file to basically load a DLL in. Typically, when a DLL is being loaded, it will first look for in the system 32 process to make sure that DLL is there, and if not, it will go somewhere else. With this manifest file, it can dictate to look in a different direction for a system level binary or DLL. This was done as a way to ensure that in older versions, as they move from like XP to 2013 2003, 2008 server, that any type of legacy stuff that required older functions could still be loaded in just with a manifest file. By doing so, we can actually register a DLL and say, hey, go and load this one first. Go here and do this. It also doesn't require the system to fully register it because of this manifest file. So with all of that, I'd like to kind of do a few demonstrations. So the first one is the binary mode, using this new feature, the process injection. So as you can see, we have our PowerPoint. And if we go to the properties, we can see all those attributes that align with, hey, this is PowerPoint. We also can see it's been signed by Microsoft, so it has a digital signature. So when we double click it, what we should see here is not actually PowerPoint calling home, but a new process. So we have effectively unhooked the parent process, spawned another process, and unhooked it before executing and injecting our shellcode. And we can run commands without being prevented or detected. We see a call home, and we can see the results of our command. Another example, this DLL side-by-side loading. So here we have this W script. So once again, it uses that registry free com. So it's going to drop a DLL and then load it in to memory. So you can see right here the private memory is going up. That's because that DLL is being loaded in. And once the DLL is fully loaded in, the shellcode will then run and our beacon will call home. And with that, we can then interact without being blocked or detected. Once again. So what can you do? Ultimately, there is no easy fix. A lot of these remediations require a massive redevelopment or redesign of the products because of the fact that they've systemically lived in userland hooks. But that's not doesn't mean that these products are bad. I want to really stress that these products are extremely valuable. And specifically, if you're a blue teamer or someone that works in an organization, I want to stress this enough. You shouldn't be worried about it or throwing your products out. Because at the simple point, in order for us to be able to do any of these types of activities or execute malicious code, we have to get access to an endpoint. So if you have a good defense in depth strategy, such as, strong password policy, patch management cycles, MFA, all that stuff, it makes it a lot harder with all those layers for an attacker to get to the point of being able to execute code on your endpoint. Quickly, just a summary of all the new features that will be released today. Added support for custom attributes. So as I mentioned before, that attribute list, ScareCrow has a large database. However, if there ever is a need, you can now use your own, depending on the situation. We've also added a whole new list of DLLs for those attributes for the WScript loader option. And this is partly due to a certain EDR product who tried to write some signatures and rules based on the fact that there are two of the same DLL loaded into the process memory. You can clearly see there's two of them. So by changing a few things around, we were able to bypass this control by looking at DLLs that normally would never be loaded into WScript, and this circumvented that detection rule. As I mentioned also previously about patching ETW and process injection, that new loader option, MSI exec, and shortly afterwards we'll be releasing a wiki attached to the project on using different commands, evasion, understanding some other specific details about the nuances of commands and everything like that to really help elevate a simulation or exercise. Hoping to get this done shortly afterwards, however, it will not be in this release today. So I provided a link to the ScareCrow repo if you want to check it out, as well as the code signing tool Limelighter. If you have any questions, after this conference or down the road, you can reach out to me on GitHub or Twitter. But at this point, I'd like to say thank you for your time, if there are any questions.